Hey everybody, this lesson is testing differences between the means, just like the last one, but this one is the population standard deviations between the two samples are not known, okay? All right, so let's go ahead and get started. So conditions for this is a t-test, obviously, because the standard deviations are not known, so the population standard deviation 1 and 2 are unknown, so that's why we do a t-score. So the other conditions are that they're random, they're independent, and they're either normally distributed or both sample sizes are greater than or equal to 30. All right, so here's our groovy standardized test statistic. Now remember, the null hypothesis always includes the equals bar, so mu1 minus mu2 is always going to be 0 right there. Okay, and this is our sample mean minus our second sample mean, and this is our standard error. Now, depending on whether the variances are equal or they're unequal depends on this guy right here. So if the variances are equal, then it's going to include this r hat or sigma hat or whatever right there. So this r hat is this. So it's going to be the sample size minus 1 times the standard deviation squared plus the sample size 2 minus 1 times its standard deviation squared, and then the denominator is the sum of the sample sizes minus 2. Okay, and then so our standard error becomes that this big old guy right here, and it's really not that bad, you guys. Sample size minus 1, standard deviation squared, sample size minus 2, standard deviation squared. Add them together and then add the two sample sizes minus 2, square root all that. Anyways, that goes right there. 1 over sample size 1 plus 1 over sample size 2. We do that, square root that. And then the degrees of freedom is this denominator right here. So n1 plus n2 minus 2. Now if they are not equal, that's when the variances are equal. When they're not equal, then there's our standard error right there. So this is what goes in the denominator right here. Okay, so we're either going to do, when the variances are equal, we'll do this times this. And then when the variances are unequal, we'll do just this, the first standard deviation squared over the sample size plus the second standard deviation squared over its sample size, and then square root all of that, okay? So then our degrees of freedom is either n minus 1 or n, whatever, the sample size minus 1, and you take the smaller of the two, okay? This is when the variances are not equal. Okay, so let's try one here, okay? So the results of the state math test for random samples of students taught by two different teachers at the same school are shown below. Okay, so here's the mean of teacher 1 and the sample standard deviation, and here's the sample size. Notice that's less than 30, so we got to look for the word the population is normal, and that's where it says it right here. The populations are normal, okay? And then here's the second mean, the second sample standard deviation, and the second sample size. So can we conclude that there is a difference in the mean math test scores for the students of the two teachers? Okay, so we're going to use a 10% significant level. Right here is important. This is 2. Assume the populations are normally distributed and that the population variances are not equal. Okay, all right. So the claim is there is a difference in the mean test scores for the students of the two teachers. So that's our claim right there. There's a difference, just means they're not equal. So this is a two-tailed test, okay? So the null is that they are equal. So we're going to try and prove that we can reject the null, otherwise we'll just fail to reject it. So because the variances are not equal and the smaller sample size is 8, then our degrees of freedom is going to be 8 minus 1. Okay, and because it's a two-tailed test with degrees of freedom of 7, and our standard or our significant factor of 10% right there, the critical value. So if we go down to 7, and I'm looking in the back of my book right here, and then we scroll down to the degrees of freedom of 7, and then look under the two-tailed test for 10%. And can you find these critical values right here? Okay, so then that just tells us that our rejection region, when we calculate our t, is anything to the left of negative 1.85 and anything to the right of positive 1.85. 895. Did I say 85895? Okay, we just slide that up. Okay, and because the variances are not equal, this is the less cumbersome of the two formulas. So sample standard deviation squared over the sample size, and the other sample standard deviation squared over its sample size, and then square root all that. Okay, so if we do all of that, there is our denominator. Remember, that's the denominator. So our standardized test statistic is going to be 473 minus 459 minus, remember this is going to be 0 over this right here, okay? So if we plug all that in right there, we get about 0.922. Okay, is that in the rejection region? Okay, so the rejection regions are to the left of negative 1.895 or to the right. Okay, always draw this. Some of my students are not drawing this and they're losing points, easy points. So draw the figure, standard deviation 1, 2, 3 on the right and 3 on the left. This textbook likes to do 4 on the right and 4 on the left, and that's okay. Okay, so 1.895 is just right here, and then negative 1.895 is just right there, and then 0.922 that we got is right there. That does not fall within the rejection region. Okay, so because it does not fall in the rejection region, we're going to fail to reject the null hypotheses. Always wrap it up with, don't just say we're going to fail to reject the null and then stop. So always interpret that in the context of a problem. So there's not enough evidence at the 10% level of significance to support the claim that the mean math test scores for the students of the two teachers are different. Okay, all right, so let's try this one. Now notice this one, the population variances are equal. So this is going to be that bigger of the two formulas. So a manufacturer claims that the mean calling range in feet of his cordless phone is greater than that of the leading competitor. So you perform a study using 14 randomly selected phones from the manufacturer and 16 randomly selected similar phones from the competitors. Notice these are totally independent of each other. Now they're less than 30, so we're looking for populations being normal. Right here, assume the populations are normally distributed. So at the 5% significance level, can we support the manufacturer's claim? Okay, well, the claim, you guys, is that the mean calling range of the manufacturer's cordless phones is greater than that of its leading competitor. So that's greater than, that is our null again. So we're going to go ahead and say that the null is the mean of the first one is greater than the mean of the second one. So the this is the alternative. So the null always has the equal, so it's less than or equal to. So we're going to see if we can reject that. Okay, so here we go. So because the variances are equal, then our degrees of freedom is n1 plus n2 minus 2, which is 28. Okay, because 14 plus 16 is 30. 30 minus 2 is 28. Because the test is a right-tailed test, because it's greater than, it's a right-tailed test, and with our level of significance at 5%, so go down to degrees of freedom of 28. Make sure you're on the one tail, and then you'll find that your t-score is 1.701. So the rejection region is anything to the right of that. Okay, so here's our formula. Here's our samples, or here's our population standard deviation hat thing right there. So this one's going to be 14 minus 1, which is 13. Okay, times 45 squared. This one's going to be 16 minus 1, which is 15 times 30 squared, and then 14 plus 16 minus 2 times, and square root all that, 1 over 14 plus 1 over 16. Okay, there we go. All right, so if we crank those out, I did them separately and got that, and I got this to be, remember, this is our denominator right here. Okay, so the 13.8018. Okay, so here we go. Our standardized test statistic is going to be the difference of the sample mean, so this guy minus this guy. Again, this is minus 0 because this one always has the equal one right there. So when we plug that in, we get about 1.811. Okay, now if it's to the right of 1.707, here it is. Draw the curve. Okay, so 1.7 is just to the left of 2. So here's our rejection region, and so 1.707 is just a little bit right here, and then our t-score that we got 1.811 is to the right of that right there. That is within the rejection region. So because it's there, we should decide to reject the null hypotheses, okay? And don't stop there, interpret that. So there is enough evidence at the 5% level of significance to support the manufacturer's claim that its phone does have a greater calling range than its competitors because the null was less than or equal to. All right, you guys, so the key thing on here is, are the variances equal or are the variances not equal? That'll tell you which formulas you're going to plug in for that. Groovy assignment. Take care.